Let's talk about solving trigonometric equations using Pythagorean identities today. And we're really going to focus in on one Pythagorean identity. And first of all, when we look at this very familiar picture, what you may remember, a couple of things, is that this point here is not 0, 1, it's 1, 0. And it actually is our 0, and if we come around full circle, we get the 2 pi. We've got the pi over 6, which has the values of radical 3 over 2 and 1/2. We've got the pi over 4, which has the order pair of square root of 2 over 2, square root of 2 over 2. We've got pi over 3, which has the values of 1/2 and the square root of 3 over 2. And then we have our other quadrantal here. It's at pi over 2, and we went over 0 and up 1. Something that you might find helpful, even though I'm not going to do it right now, is putting in the tangent values beside those points. Because tangent still seems to be a function that we're struggling with a little bit. But that's kind of a backwards idea, something that we've worked with in the past. And now what I want to do is I want to expand on it, and starting with the fact that the Pythagorean theorem is a squared plus b squared equals c squared. And if we think really far back to when we started trigonometry, what happens is we talked about drawing triangles in our circle. So we might pick, let's say, pi over 3. And let's draw in our triangle. And notice how we just made that triangle a right triangle. But where we came up with the 1/2 and the square root of 3 over 2 is we said at the origin we went over a half, and then we went up the square root of 3 over 2. In other words, what we said here is that we went the x value, and then we went up the y value, and our unit circle has a radius of 1. That's our hypotenuse in our triangle. Well, what function is represented by the x in the unit circle? And it's cosine. So, and I'm actually going to put theta in there for that. And what function is represented by the y in the unit circle? And 1 squared is 1. And this value right here, cosine squared theta plus sine squared theta equals 1, is called a Pythagorean identity. I'm fine if you remember it that way, but in general, if you look online, if you read a math book, it tends to be that sine is the first value. Sine squared theta plus cosine squared theta equals 1. I'm not quite sure why. But from this identity, we can come up with 2 more that are helpful for us when we're solving equations with Pythagorean identities. The first one, if we take sine squared theta plus cosine squared theta, if we subtract cosine squared theta both sides, and we end up with sine squared theta equals 1 minus cosine squared theta. And we do the same kind of thing with sine. I'm going to just write down the identity again. Sine squared theta plus cosine squared theta equals 1. Well, we subtracted cosine squared from both sides. We can subtract sine squared theta from both sides. We end up with cosine squared theta equals 1 minus sine squared theta. In general, the one to remember is the sine squared theta plus cosine squared theta equals 1. And then all that you have to do for your second one, solve for sine squared. And your third one, solve for cosine squared. But again, in terms of memorizing, it's memorizing the sine squared plus the cosine squared equals 1. So once we have that identity, we're going to use that identity somehow, in some format, to help us solve our equations. And notice that the directions say, give a formula for all solutions. And that means that we either are going to add the plus pi k or the plus 2 pi k. Which I want to keep stressing that as we sometimes are going to be limited to have solve for angles between 0 and 2 pi. But then sometimes we want the all solutions. And the all solutions, when you see that, should indicate the plus pi k or the plus 2 pi k. So as we take a look at this first example here, sine squared x plus cosine of x equals -1. First of all, we have two different functions in here. And we need to combine them into one. So what I see in here is that we have a sine squared. And our Pythagorean identities are sine squared theta plus cosine squared theta equals 1. We can rewrite this. And again, within this example, what we want to do is we want to rewrite it so that we only have one function instead of the two. Sine is a function and cosine being a function. So if we look above in our box here, what it says in blue, it says sine squared theta equals 1 minus cosine squared theta. So instead of writing sine squared theta down, we're going to fill in sine squared theta with 1 minus cosine squared. And in this problem, we were writing x. But if you write them all in thetas, that's fine. And then we have plus cosine of x equals -1. Again, what we did, we substituted in the 1 minus cosine squared x that came from the Pythagorean identity, and now we want to solve this function. Well, we've got a couple issues here. The first issue that stands out to me is that it's negative cosine squared x, and it's really much easier to have positive cosine squared x. But maybe for you, what you might want to do is move this 1 over to the other side. And I'll fix that negative cosine squared. But now what we have is we have negative cosine squared x, and I should have written this down here. 1 plus 1 is 2. And then we have our plus cosine of x. That's equals 0. And what we've accomplished so far is that we have all of the functions on one side of the equation, but we have a couple of issues. One, we need to write it in descending order. That's the first issue. So if we write it in descending order, we've got negative cosine squared x plus cosine of x plus 2 equals 0. But once again, the problem with this is that cosine squared is negative. What we can do is we can change all the signs in there. If you want some work to support that, divide this by -1, and divide this by -1, and divide this by -1, and divide that by -1. All that we're really doing is we're moving negative cosine squared over here to the right side of the equation. But ultimately what happens now when we do that is we end up with positive cosine squared of x plus cosine of x. And you're going to correct me here and say, Ms. Stanhope, it's not positive, because positive cosine divided by negative is negative, and then positive 2 divided by negative 1 is negative 2, and equals 0. And now this should be in the format that's familiar to us. We are going to have to solve by factoring. And when we solve by factoring, we let u equal cosine x. Whatever the function is in the problem, that's used to help us factor a little bit easier. So this becomes u squared, substituting in the u for the cosine, and it's cosine squared, minus u minus 2 equals 0. And then we can split the middle. The number for that u is a 1. And the factors that we're going to use, it's 1 times 2 is 2. And those are the only factors. When we look at this, we need to combine to be negative 1. So this is 1 minus 2. And u squared plus 1u minus 2u minus 2. If you've been doing practice, if you've been doing your online assignment, this is a pretty common factoring. We're kind of limited because our functions on the unit circle only have certain values. But now what happens is we've got this group and we've got this group. So our greatest common factor is u, and we get u plus 1. Watch out, because we're factoring out this minus here. And in fact, our greatest common factor is 2. But when we factor that out, we get u plus 1. Negative 2u divided by negative 2 is positive u. Negative 2 divided by negative 2 is positive 1. And then we have been able to factor here. We have u plus 1 and u minus 2. And what's been suggested to me is that I solve this here before we put the value of cosine. I think yes, put the value of cosine back into our function. It doesn't make any difference. So this is u plus 1 equals 0. And probably the reason that people are advising me to do that is because we don't show work. A lot of us don't show that step there, and that's fine. But we end up with u equals negative 1. And over here, u equals 2. But once again, what we have on this problem is we're not solving for u. U is representing cosine of x. So we need to put that value back into our function. And then we need to ask ourselves, where on the unit circle does cosine equal negative 1? And yet again, I want to suggest to you that you maybe draw a mini coordinate plane on your paper and you put in these values. Here is 1, 0. Here is 0, 1. Here is negative 1, 0. And here is 0, negative 1. Cosine is the x value. So where is cosine negative 1? Well, it looks like we get x is pi. And that's the only value. Remember, we're doing the general formula for all solutions, so it's either going to be plus pi k or plus 2 pi k. Which one is it? Plus 1 or plus 2? It's actually 2. Going to go all the way around to get there. Okay. Now over here, I kind of got lost on here. It's cosine of x equals 2. But where does cosine on the unit circle equal 2? And it never does. So once again, what some people like to do on this part is they like to write no solution, which we do have a solution to the problem. It's the pi plus the 2 pi k. Sometimes people just cross it out there. Our only solution for this problem in terms of the most basic of the angle is pi. And then we can take in those revolutions of 2 pi k to come up with multiple coterminal angles on the unit circle. So sorry, I did a lot of work on that one, maybe a little bit more work than I normally show. But as we flip our paper over, once again, let's think about our Pythagorean identities. The nice part is, on the notes, we can just flip back and we can write them down. But let me stress to you, knowing sine squared theta plus cosine squared theta equals 1 is really important. The other two identities, when we solved for sine, we ended up with sine squared theta equals 1 minus cosine squared of theta. And we also solved for cosine squared of theta, which is 1 minus sine squared theta. And now what we need to do is we need to solve this problem. And our first step is to try to rewrite the equation so that it's all one function. We've got sines on the left side and we've got cosines on the right. But we've got two sines on the left and we only have one cosine on the right. So let's fill in cosine squared with 1 minus sine squared theta. And then everything is written in terms of sine. We have sine squared theta minus sine of theta equals 1 minus sine squared theta. Well, let's put everything on the same side of the equals. We can add sine squared theta to both sides. So we do. This is 1 sine squared theta plus 1 sine squared theta, which is 2 sine squared theta, minus sine of theta. And not only should I have subtracted or added the sine squared, but let's move the 1 over also. Equals 0. Should look fairly familiar here. And once again, now that we have everything written in terms of one function, let's let u equal sine of theta. And that's just a technique used to help us factor a little bit easier. So this is 2u squared, filling in the u for sine, minus u minus 1 equals 0. And we're going to split the middle again, so it's going to be 2 times 1, a pretty popular value there, which is 2, because the only factors of 2 are 1 and 2. And it's going to be 1 minus 2 to give us the negative 1u. Just because the 1's not written, I know it's out of sight and out of mind. Don't forget about it. So when we fill this back in, 2u squared plus 1u minus 2u minus 1. And if you flip the minus 2u and the 1u around, that's fine. You're still going to end up in the same place with the factoring. In our first group here, in my particular group, we factored out a u and we've got 2u plus 1. Watch out, because it's minus here when we factor. So And when we factor out that, it's really minus 1 is our greatest common factor. Negative 2u divided by negative 1 is positive 2u. Negative 1 divided by negative 1 is positive 1. And consequently, now we have it split. We've got 2u plus 1 in both groups. And then we have a u minus 1 that's left over. The u in front of the parentheses, the 1 that's in front of the parentheses, including the sign. And like I said, maybe you go directly and say, oh, I know u equals negative 1/2 and u equals 1. That's fine with me. You don't have to show my next steps here that I'm going to show. But this is 2u plus 1 equals 0. And it's u minus 1 equals 0. And then we subtract. So we get 2u equals negative 1. Divide both sides by 2. So there's the u equals negative 1/2. And over here we add the 1, so u equals 1. Remember, we don't care what u is. We're looking to see what u represents, which is way back here. It's the sine of theta. Now what we need to fill in is that this is the sine of theta equals negative 1/2. And over here, it's the sine of theta equals 1. And then we might take out our left hand and try to figure it out that way. 1/2 is going to have one finger below, which is going to be pi over 6. But we're looking for angles that are negative. But everything's going to link back to pi over 6. So all students take calculus. Well, sine is negative in the third quadrant and the fourth quadrant. What's the third quadrant angle of pi over 6? 7. And then in the fourth quadrant, 11 pi over 6. Good. Now, 7 pi over 6 is here, roughly. 11 pi over 6 is here, roughly, and actually they're totally in wrong spots. But when we draw the picture to connect them, do we get a straight line? No. And because we don't get a straight line, when we write our general solution, it's 7 pi over 6 plus 2 pi k. And it's 11 pi over 6 plus 2 pi k. And we're not done with the problem. To the right of that, we've got sine of theta equals 1. And even going back on this picture here for the quadrantals, which also seem to be giving some of us some trouble, this point is 1, 0. This point is 0, 1. This point is negative 1, 0. This one is 0, negative 1. We need where sine is 1, which is the pi over 2. And that's the only value where sine of theta is 1. So to get back around to there, we will have to add 2 pi k to that as well. So as we get ready for our last example here, we're using our Pythagorean identities. We need to write the equation in terms of one function. 2 sine squared x plus cosine of x minus 2. Well, we've got a sine squared, which has Pythagorean identities. Cosine of x does not. We've got sine squared. So we can rewrite this inequality as 2 times sine squared, which is 1 minus cosine squared x. And again, if you chose to write theta, that's not going to bother me. plus cosine of x minus 2 equals 0. And now what we have is we have all cosines in there. It looks a little bit complicated. But let's start by distributing. We get 2 minus 2 cosine squared x plus cosine of x minus 2 equals 0. And when we look at this, like terms, 2 minus 2 is 0. That cancels out. So we have negative 2 cosine squared x plus cosine of x equals 0. And in our first two examples, we've had to split the middle. We don't have to split the middle on this one. We just need to factor the greatest common factor. Cosine squared means cosine times cosine. So our greatest common factor is a cosine of x. We're going to factor that out. We had 2 cosines. We took one of them out, so now we only have 1. Notice, cosine of x times cosine of x is cosine squared. Don't lose your negative. We had a cosine. We factored it out. We still need a place marker there. Cosine divided by cosine is 1. We didn't have to use a U substitution, just greatest common factor. I'm going to set cosine of x equal to 0. And we're going to set negative 2 cosine of x plus 1 equal to 0. And yet again, here comes a quadrantal. You may want to draw this little picture as a reminder. The 1, 0. The 0, 1. The negative 1, 0. The 0, negative 1. Where does cosine equal 0? Pi over 2. Pi over 2. And 3 pi over 2. The x value's there. But can we connect those 2 points with a straight line? And we can. So it's going to be pi over 2 plus pi k. Because we can connect with that straight line. Again, we're writing this in terms of the general form. We have to do a little bit more work on our answer to the right here. We're going to subtract 1 from both sides. So we get negative 2 cosine of x equals negative 1. It's negative 2 multiplied by cosine x, so we're going to divide by negative 2. So it's cosine of x equals 1/2. And again, using that hand mnemonic, for lack of better words, is helpful. And if we fold in our ring finger, we get 1 finger above. So that's going to be pi over 3. Where else is cosine positive on our unit circle? What quadrant? 4th quadrant. And what's the pi over 3 angle in the 4th quadrant? And if we think about that here in terms of our picture, I'll draw it in green. Pi over 3. 5 pi over 3. Can we connect with the straight line? No. And because we can't connect with the straight line, we're going to get pi over 3 plus 2 pi k. And 5 pi over 3 plus 2 pi k.